All right, so now I should be hearing myself, but I am not.
Yeah, basically, you sort of think of it as that operation is pulling.
Yeah.
The second item on the list, I believe, is the eraser.
Hi, my name is David Brody.
And then all but the last one, the rest are slightly off. It does do a little pressure sensitive. It's not got a huge.
How about now?
It's not an artist was not going off. There just aren't that many options with the line to work with.
You have the source code.
But otherwise, the only other thing that I occasionally run into is you do have to have the mouse in the window, otherwise it won't register. Because basically what it does is it then takes over the mouse. And so your mouse computer allows your.
Oh, David just joined again. Hey, David.
Hi again.
Another vintage one there. Oh, it's that one?
Yeah, it's an X61.
Holy shit.
2-core.
I haven't seen that.
Yeah, well,
Is the audio okay?
Yeah, and the battery life.
What I need to fix now is the audio coming from there. Just joining all this shit together is a bit of a headache.
Okay. Yeah, we can keep a couple of words to set up as well before. I assume that for you, this is all. This is something which you rehearsing with one person.
Yeah, I use it in class all the time. In fact, the power, yeah, right back here that has USB, so I plug straight into it, get my USB.
And if I mute this here,
Yeah, I'm not
I get
sure.
audio from there.
I'm going to talk about three more content.
I do.
Examine.
Right, that was it.
And
Sounds like it's working.
after the last.
Hi, my name is David Brody. I'm going to talk about three more content.
I decided that there were a couple of diagrams that normally would be easier to do this way.
All right.
Also, I kind of wanted to show the document aspect. And so
yeah,
that's so much more comfortable. Just go, okay, here's this box now. Now what happens is this box.
Yeah, so you try to go from there, go to the emails.
Yeah.
Hi, my name is David Brody.
So I will get this one. Sorry, David, I'm speaking out loud.
Yes.
Yeah.
It actually is a form of a very old program.
No problem.
Later program.
It's run reasonably smoothly.
I'm going to talk about three more Cortex-M Inferno ports. So before the workshop
We're starting the second day of this year's International Workshop on Flat 9. And the first talk will be by David on more Cortex-M Inferno ports. And this is a remote session, and this works as follows. I'm going to playback something here that is pre-recorded. Later on, we will have a Q&A. And for the Q&A, we're going to have a Google Meet. And for that, if you want to ask questions, please come over here to the microphone. I will remind you again later, just so that you're prepared. And with that, enjoy this first talk.
Hi, my name is David Brody. I'm going to talk about 3 more Cortex-M Inferno ports. So, before the workshop last year, I finally managed to get Inferno running on a microcontroller fairly reliably. And when I say microcontroller, I'm talking about an STM32 microcontroller, which is a 32-bit microcontroller, and it's got a fairly luxurious amount of RAM and flash memory, and the processor is not a very slow thing. It's quite a performant CPU. It has 192 kilobytes of RAM and a megabyte of flash memory, and the core that runs it is a Cortex-M4 core, which has some floating point support as well. The instruction set it runs is the Thumb2 instruction set, which is a hybrid instruction set in a sense, because it's designed for code density, and so some instructions are 16 bits wide and some are 32 bits wide. It's related to the original ARM instruction set, and there is some overlap with instructions, but it's a bit more complicated than that, and it probably makes writing compilers harder than they need to be. This microcontroller has just about enough RAM for a tiny shell and some tiny programs, and I was using it to experiment with SPI to drive screens and flash memory, and in a sense you could use it as a replacement for things like Arduino, but it's a bit higher end. Maybe it could also be used for sort of, I don't know, more higher end tasks as well. Not the sort of simplest microcontroller tasks, but maybe something which is between microcontrollers and regular processors. This port is a bit like the ARM ports in the Inferno tree, except it's a bit different. And one way in which it's different is the way it does task switching. So the task switching uses this approach with these 2 functions, setLabel and goToLabel, like many of the other ports. But the way that this is done for this port is a bit more complicated than the regular ARM ports. And this is really because for the ARM ports, they can perform tricks like changing processor modes. So if you have a timer, for example, and an interrupt fires as a result of the timer, an exception is raised on the processor. And as a result of that, on classic ARMs, you would be in a particular mode. And what they would tend to do to handle this would be to switch into a regular mode, I think supervisor mode, and then perform some task switching as normal. But in the Cortex-M4 cores, it's not really possible to switch between modes in this kind of ad hoc way. And that's because Cortex-M4 cores have 2 processor modes really. One is a mode for running normal code, which is thread mode, and when exceptions occur you have code running in handler mode. And there isn't really a way to switch between the 2, so you have to basically return from an exception to get back to thread mode. And this is where things are a bit different to the classic ARM ports, because what we do here is we return into thread mode and then we run the code to switch the tasks. You have to be a bit careful with this. I'm not sure I've really covered all the corner cases, but it seems to work, and it probably needs a certain amount more testing. I started writing a documentation for this that I put on GitHub, and it would be good if people with expertise in that kind of ARM or thumb processor area could look at it and sort of tell me if there's anything I've really done wrong, or ways in which it could be done better or made more robust. So last year I talked about frozen modules, frozen limbo modules, and this was basically a way to reduce RAM usage at runtime by taking disk byte code, and instead of having it processed when modules are loaded and run, pre-process it at compile time, keep it in flash memory as much as possible, and yeah, basically just try and reduce the amount of effect on RAM usage, reduce the number of allocations. So one side effect of this was it also reduced the startup RAM usage, because various data structures that would otherwise be copied into RAM at startup no longer needed to be copied into RAM, and so they could be kept in flash memory. And this was an interesting thing for me, because I hadn't really thought about just trying to reduce the overall startup cost, and it made me start to think about ways to reduce RAM usage just generally. So one of the ways I looked at was one that was already in the toolchain, which was an option, a -T option in TL, to allow string constants to be compiled into the text section of the binary. So I looked into this and tried it, and it didn't work for some reason. And so I started to look at it in a bit more detail, and I found some ways to tweak it to make it do something which looked reasonable. And it turned out it had a fairly large effect on the RAM available. In one case that I looked at, it increased it. It basically doubled the amount of available RAM. But although this sounds quite substantial, this approach overlaps with other approaches that I was taking, like the frozen module approach, and so the effect isn't typically as large as that, but it's still significant. And the other side of this is it also really complements the frozen module approach, because this basically just reduces the startup RAM cost, whereas the frozen module approach isn't made redundant by this, because that still reduces the runtime RAM cost. It reduces the number of allocations. Another approach about saving memory, it's not really so much saving memory per se, but it was an experiment to just reduce the number of memory pools in use. So there are 3 memory pools usually in play: main, heap, and image. For our purposes, image is not really very useful because we're not using a display. And usually what has to happen is we decide in advance, at compile time, what the proportions of what the memory proportions are for the main and heap pools. And this is fine for large systems, but for systems with not very much RAM, that can cause problems, because you could run out of one or the other of those pools fairly easily, even though there's still free memory in the system. And in this case, if we just use one, if we basically alias the heap and heap pool to the main pool, we just have one pool and all the allocations come from that. I'm not really sure how safe this is. I realised that you really need to kind of make sure that the main pool doesn't run out of memory. So I suppose there's the danger that certain things that would normally use the heap pool could exhaust the main pool, but it at least allows some things to run on smaller systems that would otherwise be not possible. Another memory saving approach that I briefly looked at was finding constant structures or immutable structures and moving them into the text section as well. And I had some difficulty with this because it's not very easy for me to see how to do that with the toolchain. I spent some time looking at the compiler and the linker loader just to kind of see where information gets propagated and if I could pull things out at certain times like the string constants are. So in the end I just resorted to a quick hack to check symbol names for things which I knew were read-only, and it turned out that if I move some things like lookup tables into the text section, it saved a few kilobytes more. So it may or may not be worth it, but it's useful to look at this a bit more, really, because things add up, and for small systems that's quite useful. So another area that I was looking at was just updating the toolchain for things like floating point instructions. So Cortex M4 cores have I would say modern ARM instructions for floating point. Unfortunately they're typically just single precision, and Inferno uses double precision. So the question is how useful they are. It turns out that some of them sort of overlap, so moving doubles into and out of memory, you can have instructions for this sort of thing, even if double precision arithmetic isn't supported. In any case, I borrowed a lot of code from 5L, moving it into TL, and I had to convert what it generated to thumb2 representation. I mean, really, I think with this you're just swapping around 16 bits, the first and last 16 bits of a 32-bit instruction, which is not particularly helpful. The way I did it was arguably not the best, and it could be made a lot closer to 5L. There were a couple of other issues. One of them was to do with converting double to long, where the endianness for the doubles was somehow different for thumb2. And I think there was also a case where there was a missing definition for a temporary floating point register, although I may have removed that. Also, what I had to do was disable registerization in libmath to avoid a compiler issue, and this may be also a problem that faces other ports as well. And with floating point instructions, the other area we have to look at is how to implement or how to handle unimplemented floating point instructions. So for many of these Cortex M4 cores, they only support single precision instructions, even though there is an overlap with double precision for certain operations. So there needs to be code to handle undefined instructions, and this was done by basically taking the existing ARM implementation and creating a variant for thumb instructions. And since they share the instructions more or less, this was quite straightforward. And then it was a case of testing that they did what they were supposed to do. So I created a simple test program to perform various different kinds of instructions. And I also, basically created more decorative and frivolous tests for this as well. And there are some notes and commentary about the way I handled this on the site that I mentioned before, where I'm trying to document parts of the implementation of these ports, and also in the diary that I keep for things that I do with Inferno. So about these new ports of Inferno to microcontrollers. All of them are ports to SparkFun micromod boards, but they could be easily adapted to other similar boards. It's just that it was convenient to use the micromod system for this because the processor boards and the carrier boards are interchangeable. So the first one I looked at after the STM32 was the Atmel SAMD51, and this has 256 kilobytes of RAM, which is arguably a better starting point for porting Inferno. I didn't get into porting Inferno to this very well when I started, and ended up going off and looking at the STM32 instead because I found it a bit daunting. But once I'd done the STM32 port, I realised that this one wasn't quite as frightening as I thought it was. So actually getting it to work was a lot quicker than I imagined. The next one is the Artemis module, which has an Apollo 3 core from Ambic, and that has 384 kilobytes of RAM, which is quite a bit to play with in many respects. It gives you a bit of freedom to experiment. It has a Bluetooth module, and I haven't really figured that out yet. I've been looking at code in the Arduino libraries and framework because they have examples for how to try and do various tasks with Bluetooth. The Teensy is actually a bit more, a bit of a bigger CPU. Has an IMX CPU, which is actually more like an SoC, and it's a Cortex M7 core, which is somewhat higher level than the M4 cores that I've looked at. It has a megabyte of RAM, which is pretty useful, gives you room to stretch your legs, and double precision floating point support, which actually means you don't really have to do anything at all with emulating undefined instructions. Some issues remain with all of these. The Teensy has some issue, I think, occasionally with lock loops, so I need to really look into that a bit more. And the SAMD51 probably has issues, but I can't really investigate those anymore because the board I was using stopped working. I've tried to document as much as I can of the way the implementation works for all of these, and I've provided links to all of these ports in the documentation that I've been writing. So alongside porting to these other microcontrollers, I've also been looking at the different peripherals, the different hardware buses and things like that that each of them supports. The first port, the STM32, obviously has some support for things like the UART and status LED. I got into doing things with I2C and SPI, so external flash memory, and doing things with ePaper. I didn't really do very much with the SAMD51. UART and LED were basically there at startup just to test it. I was doing things with USB and then managed to cause the thing to fail, possibly. The Apollo 3 on the Artemis module, again, the usual things to get going with, and I then started bringing across support from the STM32 to do similar things, except I also looked at an LCD screen as well. I haven't really done as much with the Teensy. I think that is more of a platform for potentially messing around with the just-in-time compiler, given that it has a lot more memory to play with. I did initially start looking at the just-in-time compiler on the Apollo 3, but I'm not sure I had enough memory to play with there. And the implementations of how these devices and how this hardware is handled can be quite similar between the different peripherals and on the different ports. And so, yeah, it's quite interesting to play with bits of hardware here. A lot of this is handled with file systems, and there are existing file systems you can just use for things like I2C, also I think SPI. But for many of these things where you have a screen, it's quite interesting to think about creating a file system where you expose, let's say, a data file that you just write to, and maybe have some sort of higher level code to actually send the data to the device, instead of exposing the SPI interface directly. It's arguably more rewarding to do things with things like e-paper, especially with the devices like the Artemis module, because that's supposed to be quite a low power device, and so it makes you consider applications where you could build solutions which were a very low power. With 3 new ports, there's a certain amount of duplicated code between them. This is because when I create a new port, I typically take one that already works and remove board specific files from it, just keeping the core files and the build files, and just try and get it to work. But this means that there are common files to all of them, or there were common files to all of them, and a fair amount of common code. And what I wanted to do was really just tidy that up and have a common place for all the, for example, Thumb or Cortex-M code that they could all share, and so they wouldn't have to have individual copies. So I created a Cortex-M branch for this, and I put common code in a Cortex-M directory, like the historical SA1110 directory for all those different boards and devices that had strong arms in them. The SAMD 51 port is still separate because the board that I have no longer works, and I don't really have much desire to revisit that at the moment. At some point, if I get another board which is compatible, I may merge it in with the others. But you can check out the Cortex-M branch to see what I've done, and hopefully this will make porting new boards, or porting Inferno to new boards that are related to these, slightly easier than it would have been. So what's next? Well, the first thing I'd like to do is measure the sizes of read-only and writable data structures. This should help me figure out how much more memory I can save and how much more RAM I can play with on various microcontrollers. So this means basically looking at ways to keep read-only data in flash memory. One of the other things I'd like to look at is to make the task switching a bit more robust. I'm fairly happy with it at the moment, but I have begun to realize there are things I haven't considered. So there are some things I need to look at, and I shall be looking at some of the other ports to see what they do in certain situations. Try and make sure that I've implemented all the things that I should have done. So we'll see if that breaks things and if I have to rethink how I've implemented it. Another thing I really want to do is to document how things were implemented for these ports a bit more than I already have done. I've started to do this with the collection of documents that I've put up on GitHub for things like floating point support and for task switching, but I really want to kind of broaden this out a bit to have much more information for people who want to try and do similar things. And I'd like to look at possibly doing some more ports to other related microcontrollers. It would be interesting to also to consider other architectures as well, but that really depends on compiler support. I know that there is some RISC-V support, there's a tool chain for that, and it would maybe be interesting to look at the extensor architecture as well on the ESP32 processors. Finally, there are some resources that you can look at. There's a related paper for these slides, which contains a bit more information, especially about memory usage. I created a site which I called Inferno Ports. It's just a GitHub site really, that contains a list of different ports, that not just the ones I've worked on, but also the general Raspberry Pi port. It contains links to them, links to the instructions for building them, and also in some cases links to downloadable files to actually install on them. And there's a related Inferno Ports documentation site which tries to cover the implementation of, well, especially these Cortex M4 and M7 ports. I also have a diary which I update from time to time to help keep me going with Inferno, and I've talked about some of the issues that I've mentioned here in that. And there is also my presentation from last year, which gives a bit more background information on the work that I did with freezing Limbo modules. Thanks very much for listening.
Now comes the interesting part, where we will see that we get Google Meeting working. So, David, can you hear us?
Yes, I can hear you.
Excellent. I'm just not hearing my own voice loud enough, so let me check here. Do you hear me loud and clear?
Yeah, I can hear you.
That's good.
We can just speak up in this room.
Sorry.
We can just speak up.
Yeah, not very. Hang on a second. Almost has to be a bit complicated sometimes.
Yeah.
So while I'm talking to myself, this currently means that people on YouTube don't actually hear much. So same for the recording. It was good before. or what's something. Can somebody do me a favor and join YouTube and see how loud I am? Oh, how about now?
Hello?
Hi. You should even hear me much better now.
Yeah, much better.
Okay. Yeah, switching input sources works. All right, so does anyone have any questions? If so, then please come here and take the microphone.
So I've played around a lot with these kinds of embedded systems, and I'm very curious how you're actually getting the code onto the devices. What kind of tool chain do you have to flash the boards and so on? And even better, is it possible to run it on Plan 9?
Okay, so to get the code onto each of these boards, it's usually fairly straightforward because they usually have some kind of bootloader that lets you use either the UART or they do something with they typically have USB connections or USB-C. But it's basically, I think, a UART or serial connection for all of them, even if it goes via USB. Trying to remember, it's different. Unfortunately, it's different for all of them. But some of them do use some fairly standard tooling, this DFU stuff. And as to running things on Plan 9, the tool chain probably runs on Plan 9. And I think someone has been pulling stuff back from the Inferno TL, for example, back into 9 front, I think.
Yes, I think I ended up pulling the thumb linkers and compilers from back into 9 front, using it for targeting the GPA, and I ran into that same problem that you did about wanting to classify these global data structures as read-only, so that you could put them in ROM instead of having to load them into RAM. As a lot of disparity in the amount of size for both of those. What we ended up discussing, and we never ended up implementing, was finding, carrying the information about what was declared as constant. I know it's not typically something we do in the code as is, but it might be useful for this application about preserving the information, having things marked as constant. Okay, that goes in the read-only data segment. And that's just something we were thinking of. So I was kind of curious to see if you had considered that, or kind of that chain of thinking for that.
Yeah. What I did was I initially went into it and looked at the compiler. I'm going to say the compiler. I think I was looking at TC and TL basically. And what I found interesting was that, is it constant and static are both considered garbage words or something. So you don't really get the information about those once the code gets as far as TL, as far as I'm aware. I then started to think about, I think I have some diagnostic code where I look at the sizes of things. And I started to do tricks where I was basically just looking at symbol names. So for example, you have all the error strings, which are not constant strings. When I was talking about constant strings in the presentation, they're basically literal string constants in the code. But for example, the error messages, they are defined as character arrays somewhere. And I realized if I did a quick hack where I did a string comparison on symbol names, you can pull all those into the text section. And I did that with lots of different structures. I started identifying things by the names and was seeing what would happen if I moved them out of data into text. And for some of these things, they need to be written to at runtime, so that breaks things badly. One thing I was thinking about was basically trying to reintroduce some kind of qualifier that you could add to the code to say this is something that never changes. I think at last when I looked at like Arduino programming, they had this progmem macro or something, and you could probably decorate lots of things with that. But I don't really want to go into the general Inferno code base and just start adding something like that.
I wonder whether the compiler could actually mark things as having been written, since it does in some sense know it has to compile the code. It knows when something's in a writable context in an expression, for example. And if you get to the loader without that attribute being set, you could then decide to put whatever it is into the your flash memory or read-only memory or whatever it is.
I think that's what I wanted to. I just couldn't see how to do it in a very quick way. I didn't really. I have to say I don't have a very good understanding of the way the compiler works. So I was effectively tracing through a lot of symbols and looking at data structures and trying to see if it has that kind of information and passes it through. And I think there's this kind of barrier through which it doesn't propagate some of this. But I don't know. I think it takes a lot more study before I can understand that.
Hello?
Hello?
Oh, sorry. I've been talking apparently to empty space. Probably not for the first time. I was going to say that the advantage of having the compiler do it without attributes is that, well, first it will then find them all, or a great many of them, and you won't have to worry about adding the attribute. The other is that const has the disadvantage, like async await, of propagating throughout your type system the way that C defined it, or ANSI C defined it. Whereas the compiler at some stage has an AST form where the names are still visible and what you're doing with the names is still visible, so that it might not be too hard to set it up so that it marks a name as having been written to, including indexed names, or the base name of an index name, A sub B. And then the later stages, provided that information is carried through in some way, which probably isn't too hard to add, then the later stages, such as the loader, can use that information in order to decide where to put things, and do that automatically for you, without having to touch anything else. So yeah, I'll think a bit about that. I mean, it's much. One has the program in a not too bad a form at an early stage. It probably could do more along those lines to aid implementations like yours. I mean, it's one advantage of having ownership of the tool chain, really.
Yeah, I think it looks like someone tried to do something like this before when I looked at the implementation, because I think there are some enums which are not used for describing different kinds of like text or data. I think is something which I would interpret as talking about constant data or something, and it's just not used. So it seemed to me that someone had thought about this before, but not really implemented it or something. So
Yes, I mean, we went through a phase of doing some things with quite small boards, but then the targets we ended up working with commercially ended up being a little bigger, and so we didn't have to do things. In fact, even the thumb mode was only added as a kind of commercial requirement, which they then didn't pursue because it's on the target that they had. It was actually rather silly compared to the things that you're working with.
Yeah, but it's in the end it was good that it was added because it's effectively mandatory now for a certain level of processors.
Yes, indeed. I mean, at the time we were anticipating that ARM's various circuitous ways of adding more not even variants, completely different architectures for each of the processors, and then deciding that they would go with something much more conventional with the thumb stuff.
Yeah, it's quite a mess with all that now. I mean, it's almost a case that you have systems that will support the thumb mode and 64-bit, but not really 32-bit or something. It's quite bizarre, really.
Yeah, so at some point they forgot that they had a 32-bit architecture already there and then invented another one. But it's quite impressive how much work you've been able to do on that to get all that stuff going.
Thanks. It's amazing it actually works in some ways.
Right, so nobody dares to ask more questions. I can just confirm from my side. Ron has a question, but you need to get up here.
Oh,
Microphone is here. He's coming.
I guess it's on your website, but I was just wondering where you get the e-ink display.
I think I got it from, the e-ink display came from Pimeroni in the UK.
All right, so that little advice was the last question. And yeah, I can confirm from my side, indeed, it's very different with each and every vendor and chip and whatever to get code on that. It's always good to have that documented somewhere. I can tell that from the Orbit project. Anyway, thank you very, very much.
Thank you.
And we're heading on with our next talk in just a bit. Thank you.
shows off.
Yeah.
Great, of course.
All right. I see things moving more rapidly when I make noises.
Yeah, now audio is good. Okay.
Perfect.
All right, good.
Okay. All right, so I assume I'm good to start. Yeah, so with this talk, I was considering making slides, and then I decided doing the ASCII art diagrams is going to be a bit of a pain in the ass. And Brian thankfully loaned me his the setup that he does lectures with, so I can just kind of wing this, do it live, and I could go drinking last night instead of making slides. So this presentation does exactly what will probably go exactly as you expect. So I'm going to be talking about the 5V, which is basically a fork of 5E that I made to do val grindy stuff. So 5E, that's our MIPS emulator, or sorry, our ARM emulator, ARM32. It was written by IU several years ago, and it's basically it takes a binary, an ARM binary, and runs it in our system as though it was just a. It's not a full system emulator. It does the syscalls, it does the file I/O, but runs a MIPS. Why do I keep saying MIPS? An ARM binary in our system as though it was a binary on the native running on the native system. Having this in the way allows us to do a whole bunch of stuff. So I'm going to take a step back and talk about why we care about doing val grindy stuff. What is val grindy stuff? Most people here have probably written some C programs. And in C programs, you've probably seen segmentation violations, you've seen panics, you've seen all sorts of bugs where you have an array, for example, and you write to array index, you've got 0, 1, and it's a 4-element array. So you want to write to the last element, and you write to element 4. Oh shit, that's not actually in the array. C is kind of C is famous for allowing these kinds of out-of-bounds writes, out-of-bounds reads, accessing of uninitialized memory. So for example, if you have a function stack and you're calling f of 1, which does, I don't know, int x, and you do return x, or f of y, well, you push y, and then you make room on your stack and return x, which, what's the value of x? I don't know. It was on the stack somewhere. So C does very little to protect you from this. So how do you deal with this? Well, the traditional Plan 9 solution for this, it works pretty well, but it's not really scalable. Plan 9 solution, get good at thinking about this. Don't make those bugs. Now, the rest of the world kind of went, well, our programmers are, they keep making these mistakes. We need to figure out some way to help them solve them, help them debug them quickly. So there are tools out there called Valgrind, Address Sanitizer, Electric Fence, I think, was one of the early ones, Mudflap. You can come up with a whole taxonomy of them. And they all do the same or similar things in a different way. So Valgrind, for example, is wow. This I'm not good at writing. Valgrind is basically a full system emulator, or not full system. Sorry, binary emulator similar to 5E. Oops. Let me erase. Good enough. It's a binary emulator, it emulates the x86 architecture well enough to run whatever programs you need. And as it emulates things step by step, what it does is it will basically check that you're accessing things within bounds. It hooks your malloc implementation and goes, hey, are you within the array? Are you reading uninitialized memory? So that's how Valgrind works. Address sanitizer is a similar idea. But what it does is it takes the, it's actually, well, address sanitizer is slightly more interesting because what it does is it modifies the compiler to instrument the binary, where if you access something that's out of bounds, the compiler will access a shadow map. It will check whether the value's been initialized and so on. So I'm kind of grabbing ideas from both of these, and what 5e is doing is, it basically does this kind of, it does the emulation, which is nice, and then, but it uses the same shadow map idea that ASEN has. So I mentioned this term shadow map. I should probably explain what it is. So whenever you have a binary, it has several memory segments. And so actually, I'll do one more. It's got its text segment, data segment, BSS, and stack. So what we want to do is kind of keep track of the state of these segments. And a shadow map is basically, well, what if we took every byte in each of these maps, or each of these segments, and assigned a few bits of state to it? So, for example, so Valgrind does this with a single shadow map, where you cover the entire program's address space, steal a chunk of it, and put it out in the out of the way, so that if a stray pointer happens to happen, it probably won't corrupt your shadow map. In 5v, what I do is I just don't put this into the address space of the program, because this is an emulator. It doesn't have to expose everything. So whenever I access a byte, I basically take the address, divide it by 4. So I'm assigning 2 bits of state to every address. You have alloc. So every address can be either allocated or not allocated. And init, so initialized. Has it been written to before it's been read? Or has it been written to? So when you have a program that does something like x equals, or p equals malloc 3. I'll do char pointer p equals malloc 3. So I'm mallocing 3 bytes. Then I do p0 equals 1, p 1 plus plus return p4, for example. What will happen is that I will take I'll hook malloc, so I'll use the libmock to find the address of malloc. When the PC in the emulator hits that PC, I will record the return address, and when malloc returns, I'll basically say, hey, we allocated this much memory. Let me go into the shadow map and mark these bytes here as initialized, or as allocated. So you get the state of the shadow map for ... 1 0 1 0 1 0 0 0 0 ... So basically, these 6 bytes represent the state change from malloc 3. Then when I hit the P1, P0 equals 1, I'm initializing the first byte. So this becomes 1 1. The byte is both allocated and initialized. When I try to access P1++, well, I'm reading from a byte that is in the alloc but not initialized state. So the emulator goes, oh, you're trying to do something funky. Let me pause the program. And 5e has something very nice where it also serves a fake /proc. So you can just attach with ACID, debug, see what line you're at, what the state of variables are, what's going wrong. But let's assume that I find the bug, I fix it, and say P0++. OK, so now I fixed the program. And here it'll get to the state where, OK, I'm trying to return from a value from P4. P4 is somewhere out here, 0 0. Oh, shit. Well, I guess we've gone off the end of the array. You're accessing unallocated and uninitialized memory. OK, this program is garbage here, too. So we can detect these kind of memory issues using the shadow map. Maintaining the shadow map is a bunch of overhead, but the programs still run. I haven't actually benchmarked, but they run well enough that you can actually test some reasonable size programs. The compilers actually will compile running under 5e. So, although, yeah, so what are the so obviously maintaining the shadow map, you need a bunch of hooks. So you need to hook malloc, you need to hook free, but also you need to be able to handle the segment allocation or segment functions like segbreak, which is used by a bunch of programs for allocating memory that they know is zeroed, but it's also used inside the malloc. So when malloc is called, you have to disable the seg tracking so that you can so you can mark the memory as uninitialized rather than initialized. You also need to hook the other syscalls that might not be quite as obvious, like read, write, and so on, because you need to. And the reason you want that is because you want to be able to detect when the kernel would be accessing memory that's initialized or uninitialized or whatever else. The last thing that's probably, OK, so that's roughly how this works, and that's roughly the current state of what I've implemented. There are a bunch of things that are missing from this still, big ones. There's, at the moment, there's no good way for me to find the stack size for when you take a function call. So when you have your program stack and you call a function, and then you call another function, and then you write to some stuff, and your shadow map gets updated. So these values are all marked as valid because you've initialized them properly, and then you return. Well, I have no idea how much of the valid stuff needs to be cleared as invalid now. Yes?
Maybe you can track stack pointer updates.
Yeah, the big problem is that at least on ARM, I think we have a convention, but yeah, it could possibly track stack pointer updates. But then when you call the next function, well, all the stack is valid. So this is kind of the big thing that's missing. The other thing is that when you call a function, yeah, I guess stack pointer updates would work. But it's not implemented. So this is roughly the state of things. This is the whip. This is the big idea. The other thing is that there are a whole bunch of things I would love to have. Oh yeah, the other thing is that it needs to know about the ape allocator if you're ever going to run allocation function, if you're ever going to debug ported programs. It doesn't actually know about global objects or add red zones around variables. So if you have an array followed by another array, and you access this array from this pointer, but then you access out of bounds in this array, this arrays will be marked as valid because, hey, you initialized it correctly. It doesn't know about different regions. So there are a couple of different options that I'm considering. One is that maybe I waste a bunch more memory in the shadow map and basically tag each object with the pointer. The other is that I teach the compiler to just kind of leave gaps around everything. So most accesses that are out of bounds will go only a little bit outside, or most of them will only go a little bit outside of the object. So you don't get random stray pointers all over the place. Or if you do, it's because that pointer was uninitialized, so you'd already trapped the access. So this is one thing I want to do. The other thing is that if you've ever used Valgrind or ASAN, there's another suite of tools around it, like Thread Sanitizer, where it'll actually instrument and watch for atomic accesses. And from my understanding, what it'll do is it'll build a vector clock for every memory address that's been accessed using an atomic instruction or is protected by a mutex. And then if you can't establish a total ordering on these memory accesses, you've got a race condition. So if you can't use a Lamport clock to establish a happens before on every access. This would be something else to play with. And then the other thing that I would really like to do is actually throw this all away and put it into the linker. So having this running in an emulator, I'm not sure how fast. As I said, I haven't benchmarked what this 5V looks like, but Valgrind gives you roughly a 20 times to 40 times slowdown. I assume that this is probably going to be closer to 100 times just because there's been zero work going into optimizing it. It allows multi-proc programs to be tested, so there's a lot of mutex contention around just boring memory accesses. Or there's a lock around every memory. There's an RW lock around every memory I/O. So I think that putting this into the linker, teaching the linker how to actually generate the instrumentation around the memory reads, memory writes, and using a shadow map and putting a shadow map in as a separate segment would probably be a more interesting or more useful way of doing it. The other thing is the linker already knows exactly how much stack space is being allocated for each function, so it can generate a clear shadow stack operation at every function call or at every function return. Anyway, that's more or less the summary of what I've been working on. This whip feels like it's more whip than others, and we'll see. It has been useful for debugging a couple of small programs for me, but there's more work to be done. Any questions?
Yeah, very quickly. So just to make it clear, so you have full emulator, like full interpreter, you can run it on x86, so you need ARM host.
No, full interpreter. The reason it's ARM is just because we had the ARM interpreter lying around, and it had hooks in exactly the right places for every memory access where you got the bits for what the operation was, what the value was, and what the address was. So there was one place where I needed to change the code.
But you're still using the host kernel, right? For the kernel.
Uses the host kernel. You just point a binary at it, and it'll run it. It feels very much like using Valgrind.
This is for the linker idea. Would the idea, I mean, are you going to blow up the binary sizes, or are you going to do something that...
Yeah, The binaries will end up being probably I'm going to guess 2 or 3 times the size, because you need to, after every memory read, you could do some stuff where you verify, you basically float the access check up and avoid repeated ones, but it'll grow the binary size quite a bit. You'll probably, if the most naive option is you basically insert a function call or a jump to a small check for every memory access. ASAN, so address sanitizer, I assume they've got optimizations, but supposedly in production they're about 2x slower than running a regular binary, and I think that there's probably going to be, like, we're not going to hit that, because I don't think we're going to be, the first implementation is going to be naive, and we don't have the loop invariant code motion that you would have in a Clang, or we don't have the some of the other compiler optimizations that would be able to kind of go, oh, this check has already been done up here. We can just eliminate this one. We could work towards that. But yeah, 2x binary size plus. Any other questions? Nope. Okay.
Uh-oh. Okay. So little time here today. I just wanted to mention there's a memorial fund at UCalgary in memory of Andrei Merchovsky. Some of you here knew him from back in the day. That's a picture of him in 2005 when he was a grad student at UCalgary. And he was actually really well known in the Plan 9 community till, I'd say, about 5-10 years ago, when he had moved on to working from Cisco. I just thought I'd mention a few of the things he did. He actually was very early in the game of trying to push Plan 9 as a good way to build grids. And if any of you remember the 9 grid, he was sort of a core person and instrumental in starting that. We worked on that with David Prasado for a while before he went on to greener pastures. But you can kind of see one of the things he worked on here was XCPU. And then he did a really nice job when he was at Lanol on this project called CellFS. And he actually came into the URoot project early in 2012 and kind of helped that get established as a well-architected Go project. What a lot of people, I didn't realize this, didn't know. I talked to people here, I got the who is Andre. So one thing to keep in mind with Andre, if you run games, back in the day, he worked with Jim McKee, bringing games forward from 2nd, 3rd edition to 4th edition. So you run any game, you're probably running code Andre ported forward. If you run Sokoban, I believe he actually wrote that from scratch. It's one of my games I always really liked on Plan 9. But he was always pretty involved. If you look him up, you'll find him in a lot of discussions around the early 2000s. He worked with me on bringing Plan 9 as a boot target into Linux BIOS. So because he was up in the frozen north, Rob Pike once called him Nanook of the frozen BIOS. So he was sort of known to people in the Unix room and the Plan 9 core. And he continued to push on the idea of Plan 9 is a good thing to work on. So, you know, people kept saying, well, Plan 9 is dead. And so he did an article in Usenix with Lucho. And they talked about, yeah, well, fine, it may be dead in some people's eyes, but there are reasons it still matters. And they brought up things we kind of think about here. You know, it's still relevant, which I think is true when we look at some of the things we saw yesterday, and the simplicity and the other properties it has, the clarity of the code, the kind of things we all really find very powerful about Plan 9. So unfortunately, he passed on about 4 years ago now. And so we set up, or his wife set up a scholarship at the Bow Valley College. And this was for people like Andre. He came here from Bulgaria to University of Saskatchewan, and from there to Calgary. And that was tough. If you can imagine coming from Bulgaria, you know, sort of around 2000, what it took to do that was no small thing. And so Petya, also from Bulgaria, decided it would be nice to set up this fund to help students coming into Bow Valley from overseas. So there are the scholarship details. If you just search for Andrei Murchovsky Legacy Bursary, you know, I just experimented with that, and that worked. So Petya also sent a note. This bursary is in its third year. They've supported 10 students so far from places like Brazil, Chile, India, and other places. Some of the people who come in actually have young families. So this is really not a small deal to get this kind of money to these students and help them out. I'd say it's really been successful. You know, Andre would have really liked this. I was going to try not to get emotional, and I just did. But he would in 48 this fall. I really miss him. I know a lot of us do. So if you're looking for a good cause to contribute to, I think this is a good one, and it really kind of supports someone who really contributed to the community. Thanks. That's it.
So hello everyone. I'm Joel, and I want to talk to you about the GPU file system that I'm developing. And just before we get into the topic, let me just quickly tell you something about myself, because that's related. I'm a professional game developer, mostly on the programming side, but also some tech art stuff. And as someone who likes games and who's a game developer, I like real-time rendering, and I love shaders, and I like to see the different technologies that just work with them. And I miss hardware acceleration on Plan 9. So that's basically the plot line of everything. I miss hardware acceleration on Plan 9. And before we go into the topic of the file system itself, we have to talk about what a GPU is. A GPU is a coprocessor similar to the FPU or any other coprocessor that you might know. But I think it's something more than just a coprocessor. It's more complex, and it has its own memory, its own power management, its own cores, its own instruction set, actually different instruction sets per generation. And as that, I think it's just fine to also call it a separate computer, because that's basically what it is. It's initially called the graphics processing unit, of course, because it's about graphics. First 2D, then later also 3D. But it can also do much more than just graphics. Especially in the last years, we have seen quite a few improvements about indirect rendering and mixing between compute parts and the graphics parts. So in that case, it's also possible to run compute shaders. Compute shaders are basically also shaders, but they are not inside that strict rendering pipeline. It's just about processing data, basically. And that's also called the GPU, the general purpose GPU. You will probably hear that a lot, but not in this talk. I try to keep it at a limit. The GPU is also the best example, in my opinion, for the SIMD, the single instruction multiple data, because graphics are something you can just imagine. You can see it in your brain. If you think about an image, it's thousands of pixels, sometimes even way more, but it's often the same process for each pixel, and that's basically the perfect example for SIMD. A GPU can run a program 1,000 times with different data in parallel. The bigger issue about GPUs, but we won't cover that in this talk, is that you have different generations. Each generation has a little bit of a different architecture, but these are all the technical details that are just hidden behind the API or behind the driver. So in the next slide here, let's talk about the application architecture. But first, let's talk about the application, because not all applications are the best example for GPU acceleration. An application can be anything. It can be a game, it can be a mining machine, it can be an offline renderer, basically everything that profits from having huge amounts of data and has to process them with the same instructions, basically. So in this image here, you can see 3 different possible architectural layouts for the applications. The most important for us are the first or the top 2 layers. It's the application and the file system, because everything below the file system is abstracted behind the file system, obviously. So the application doesn't know about the driver, it doesn't know about the network, it doesn't know about virtual machine, it doesn't know about anything. It's just talking to the file system. And that's also the most important point here. The file system is the resource abstraction point, like usual with Plan 9 file systems, of course. And this file system interface should also remain the same across all implementations of the file system. So if you have a GPU file system for draw term, or a file system for a kernel on ARM, or a kernel on any architecture, basically, the file system interface should be the same. This also means that your application, of course, can use different GPU file systems based on what you bind there. Quite flexible. But since we're talking about the file system, it also has a big impact on performance, because our file systems are 9P file systems, and 9P could introduce a big overhead. But that's also something that we can explore in the future when we have working systems. So nothing to be worried about yet. Yeah. This slide also tells us that the scalability is in the responsibility of the application. That means that the GPU file system itself obviously can't know about the application and the use case of the application. So the application itself must scale. This can happen for games, for example, by drawing less, using culling techniques, drawing things at a smaller detail. Basically everything that we know from game dev perspective, but there are also non-game dev tasks. And those non-game dev tasks are a bigger issue because you need accuracy in the data. We're talking here about simulations or scientific tasks, statistics, whatever. But in those cases, I think that it's also fine to just get rid of the performance, basically, because slower is fine. Next, let's talk about the Vulkan, because the file system itself is very much inspired by the Vulkan API. Vulkan itself is designed by Kronos. Kronos also designed OpenGL, for example. And Vulkan is very low level, especially compared with DirectX and OpenGL. A program that's written for OpenGL can be like 100 lines, while an example in Vulkan would be like 200, 300, 400, or even 500 lines, or maybe even more. The benefit of Vulkan is that it's abstract and cross-platform. That means you have your own shader language, SPIR-V, that's also cross-platform. You can just copy that shader program from one platform to the other and it will work. And it's available on Windows, Linux, Android, Mac, and probably a few others. Yeah. The Vulkan itself thinks about shaders and buffers as objects, so that also transfers nicely to a file system hierarchy. And also have a small image for you, because that's basically what the interface might look like, or the flow is. You put your shaders and your buffer into the file system. The file system uploads and downloads data from the GPU to the CPU memory. And your shaders will be compiled and uploaded to the GPU. And of course, the commands like run this shader, run that shader, that's also scheduled by the file system. And everything is, of course, executed on the GPU itself. To get a program to work on the GPU, you, of course, need to have the program in a language that the GPU understands, so you have to compile it. And usually, you don't write the SPIR-V code yourself. You use a compiler to compile it from some GLSL, HLSL, any other high-level shader program. In this case, I have the GLSL example because OpenGL is, yeah, the next big brother from SPIR-V, from Vulkan. And this GLSL program can be compiled to the SPIR-V program. And that SPIR-V program can be handed over to the driver, and the driver will compile it down to a native program for the specific architecture, for the specific GPU. It will also upload it, and then this code can be executed. So there's lots of magic that's happening in the driver. You don't have to worry about it. Even the file system itself doesn't have to worry about that. And the SPIR-V program itself is cross-platform. It's not machine-specific. It's yeah, you can really copy it from one system to the other, and it will work. It's more or less a description of the program. So you can also use it to cross-compile from one shader language to another. Even all the variable names and everything is still there. And that's quite incredible. Also, it's not just that you get a compiled version from GLSL to HLSL, but the HLSL program will also work. There's no restriction, no limitation. So with that compiled program and a rough information about what Vulkan is and what it does, we can talk about the file system. But at this point, I just have to give you that disclaimer. It is a work in progress on purpose. There are no guarantees that it will work. There are no guarantees that the things won't change. I expect that things will change. especially the interface itself. But anyways, I will show it to you. I had a few requirements for the file system interface, especially because, yeah, I'm working on it only in my free time, so yeah. It should be simple to understand. That's one of the most important things here. It should be easy to develop applications for it, and it should be easy enough so you can also handle it by hand. So you can type in the commands manually, you can pipe in your own shader programs and your buffer data via a shell script or anything like that. That's one of the things that I want. It should, of course, also be generic enough to be portable, because Plan 9 is portable and file systems are about resource abstraction, and that's also basically portability. That also makes it plug and playable, so you can just import a file system from any other machine in your network and you can benefit from the GPU processing power. Also great for laptops or anything like that, where you just want this as a terminal and your file server or your CPU server has the power and also the GPU. And it will be GPU first, so we will only focus on compute shaders in the beginning. Here in this image you can see the rough layout of the file system. It's supposed to be in the dev folder because it's a file system, it's a driver basically, a kernel device in most cases. And this file system has its own control file that's for the whole GPU file system basically. And then it has the descriptor table, more on that in a minute. And it has its objects as folders. So you have object 0 and object 1. The one is a buffer, the other is a shader. Both of them have their own control files, and both of them have their own data files. So you can upload your buffer data into the buffer file, and you can upload your shader program in the shader file. That could look like that. You can just pipe in, let's create a new buffer with 4 bytes length and a new shader. So that we have this, I have it commented here. You have object 0 and object 1, a buffer and a shader. And to load your data in, you can just copy the data in there. Yeah, now about the descriptor table, because that's something I have to explain. It's a technical thing. It's a lot about how Vulkan and OpenGL see the resources on the GPU. Probably also DirectX, I don't know. In this case, you can see one descriptor pool, and this one descriptor tool has 2 descriptor sets, and those the first descriptor set just has 4 bindings, and those are buffer bindings. So for a shader to access a specific buffer, you just don't tell it to access buffer 0. You tell it to access the buffer that's bound to this specific binding here. This gives you the power to switch buffers basically instantly, because you don't have to wait for the GPU to copy data around. So your shader basically points to this specific pointer, and this pointer points to the buffer. The shader is bound to the full descriptor pool. So in this case, a shader could be bound to the descriptor pool 0, and the buffer is bound to one specific binding inside a set. In this case, buffer 0, the one we have created earlier, is bound to the second, or index 1, binding of the first descriptor set. This is confusing, and you will see in a second in the program. I have an example shader program for you, just so you can understand it. This is the example shader program. It's written in GLSL, and only because SPIR-V is very long and confusing, so let's just talk about the GLSL version. This is 12 lines of code GLSL, which would be like 55 lines in SPIR-V assembly. You can basically ignore anything in this program. I will just point out those three important things here. The first important thing is the first layout line, which tells our shader that it will access binding 1 of set 0. So it's basically this slot entry here, set 0, binding 1. And it's a buffer, and it holds data. That's basically what this thing here says. There's also some matching about the STD 430 here, but in this case, let's just ignore it. And the second important thing is the layout line itself, the second layout line. And this tells us that the work group that this shader will be executed in has a size of 1000 in X direction and 1 and 1 in Y and Z direction. So it's basically one-dimensional. Out of 3 dimensions, we focus on only 1 dimension in this program. And also in the third important thing of this program, we also only focus on the X coordinate of the invocation, because each invocation of the shader has its own specific global invocation ID. And that's a variable we get from the system. And out of that ID, we use the X coordinate to access the right data inside the buffer. And then you can do something beautiful with the position. Congratulations. I glanced on the workgroup with you. So let's just take a deeper look in what a workgroup is. A workgroup is basically very, very necessary and important if you run a shader on a GPU. Because you don't just run your shader program once or twice or 100 times. You basically dispatch your shader to the GPU a number of times. And inside the GPU itself will dispatch a number of invocations for that shader, for each invocation, or for each dispatch. So the application tells the GPU, for example, hey, I want you to run 100 workgroups of that shader. And the shader itself says, how big is my workgroup? That's the workgroup size. So just to give you an example, you want 1000 invocations, which is quite a lot. Not in GPU terms, but for us to imagine. You have a size of 10, that's possible. But then you also have to dispatch like 100 workgroups of this shader. Or you can say, okay, my size is 100. Then you only need like the 10 invocations or the 10 workgroups. Those two examples can be a huge performance difference, but that's also something that we don't have to worry about. That's also relevant for the application developer. You have seen that the workgroup size itself is a 3D vector, and the same also applies to the number of the workgroups. So if you, as an application, say, hey, I want you to run this shader in this amount of workgroups, then this amount of workgroups is a 3D vector. In total, your shader has this, you have seen it, this global invocation ID. And the maximum number of the global invocation ID, of course, depends on the number of workgroups and the workgroup size. So your number of invocations is those both values multiplied. And with a 3D vector and large numbers like 1000, you can imagine that those numbers can be really, really high. Yeah. And that's almost basically it. I still want to tell you about the implementations that I did, or that I didn't do. Yeah. At first, I started with the draft implementation. That's a fully CPU-based implementation. That was my implementation when I was also writing the paper. Its focus was on the file system, and I paused it because, yeah, I wanted to refine the interface just with an actual GPU. And that's why I started the drawtime implementation. It's using an actual GPU, using the Vulkan SDK. And I want to use it to verify and refine the file system interfaces and fix issues and also get nice images. And also then at that point, then we will also hopefully have something that just works, so we can use a GPU in Plan 9 software. And there might also be others in the future. I just recently learned that CPUs sometimes have their own SIMD functionality, which could be used. That's the SSE stuff and whatever, different versions, different architectures from different manufacturers. I don't know. There could also be some network implementation, hardware, whatever you want. And that's something for the future. Maybe someone else will do it. I probably can't. But yeah, so this is basically also my last slide because I don't have images of working GPUs. So thank you, everyone. And do you have any questions?
All right, so do we have any questions? If so, please come to the microphone.
Hey Joe, can you tell us more about how the GPU programs are compiled depending on the generation of the architecture? Is it something the SDK provides, or you have a separate toolkit for that? Yeah, can you a bit elaborate on that? Thank you.
Hi. As far as I know, that's basically handled inside the driver itself. So even the SDK just forwards basically part of the shader or the shader itself to the driver, and the driver will convert it to a format that can be run on the GPU. I hope that answers the question.
Yep, I see nodding.
Great.
Okay, one more question.
So how much of the complexity of the entire driver stack do you plan to expose, and what have you decided that you want to leave out on purpose?
That's a very good question. And I can only say that I don't know yet. I really hope that we can make everything available, but that's also just a question of how much time do we have, what makes sense. It's a question in like 2 or 3 years, if we even still need the graphics pipeline. Maybe we don't need that at all, because maybe everything is compute-based then. So we will see.
Great, one more question coming.
Do you have any ideas what you think the file system would look like for the graphics part of it, though, when you get to that? How to expose, like, is it going to be a frame buffer looking file, or some way of just setting up the pipeline, or what?
Especially in the beginning, I can imagine that everything will mostly be compute-based, and that the compute shaders can write into a buffer, and that buffer is basically just an image of DevDraw. That's at least something that I can imagine.
Right, looks like that's it. So thank you very much again.
Thank you.
And we're heading over to our next talk in a bit.
Okay, we good? Yeah, we are there.
Turn off the seating.
Yeah. Okay, and good. You're getting it there. All right. All right, well, let's jump in for the last talk of the day. Hopefully we have chosen this properly so that everyone is going to be so tired and asleep, no one will have any objections to anything. Yeah. Okay. So first of all, let me set up a little bit of context on what this work was about. First of all, this was all done at CoreAid in primarily around the 2013 to 2014 timeframe. So this was towards the end of the venture capital phase of CoreAid. And it's kind of an interesting look in the sense that it's what did we think we were looking at for the future 10 years ago? Because this was all in a research setting where we were really trying to ask, what is the future of storage going to look like? The idea was that certainly we do expect to see networked storage the same way we've been seeing it, and we have indeed continued to see that happen. We were wanting to find ways of avoiding, for example, the bottlenecks of the head that you would normally see in a storage environment. And we were also looking at the possibility of blurring the lines between the different types of granularities. And I'll talk about that a little bit more in a minute. But there's different ways you can sort of look at the stuff that's out there to store data on, whether you look at it as files or as blocks or whatever. And so we were wanting to blur those lines and allow for some generality there. Another thing that I wanted to do was to kind of ask the question, is walking really all that necessary? What if we just take the full path name and use that as a hash table lookup to the metadata, rather than having the hierarchical structure that we represent in the names necessarily being reflected in the disk data structures? That was one of the questions I wanted to look at. And finally, and perhaps most importantly, it annoyed me to no end that ZFS came along and called themselves the last word in file systems. Who were they to say they were the last word in file systems? They had used the letter Z. Therefore, I began going through the letters of the Greek alphabet with the plan of ending on Omega FS. As you can see, I got up to Theta. So that's kind of a look at where this comes from. Now, it's been sitting somewhat fallow, but in use exclusively in my basement for the past 10 years. And it is also running on this Pi, as we will see. So to talk a little bit about the different kinds of granularities. When we think about a traditional storage device, outside of tapes that is, we're typically thinking in terms of a random access collection of fixed size blocks. And if we present that as the resource over a network, then we get the thing that in the trade is referred to as a storage area network, and a SAN. And this was the type of product that we were producing at CoreAid. Now, the other side of the coin is, okay, maybe I don't want to think of it in terms of the raw block numbers, but I want to think in terms of named things that are of variable size, the things we think of as files. And in that sort of setting, then, if you have the other end of the network talking in terms of files, you have what we will often refer to as NAS, or network attached storage. So it really kind of comes down to a question of where is the break between the management of, if we've got an application here, is the file system management code and the storage device here, is the network between the application and the file system code, or is the network between the file system code and the storage device? This has always kind of been the fundamental distinction between different ways of doing network storage. So around that time, there was a growing interest in a type of storage referred to as object store. It was the up-and-coming thing. The predictions were in 10 years that would be everything. Obviously, the predictions did not come true. But how did the idea of the object store work? Well, the idea here was that instead of having the structure of a file system, instead of having the things like directories and superblocks and all of that kind of thing, you simply have, instead of named resources, you have resources identified by a number or a pair of numbers. And some manufacturers were even beginning to manufacture devices that spoke this. There was basically what they called an OSD, an Object Storage Device Protocol, that was coming into being, where you would always refer to something in terms of this pair of numbers. So that was the trendy direction. And in order to understand where that fit here, I essentially said, well, the reality is our file system is really two parts anyway. We've got our name management here, not MAME, name. And then we've got our storage management here. And so in some sense, what happens is, in an object environment, the network goes right here, between the names and the storage management. And so the thought was, well, really, all of these models are pretty close to the same thing. There's really not that much difference in these models. Why can't we have an appliance which simply is able to talk all three? So that was a big part of the beginning of this system. Now, in order to do that, then I need the protocols to talk them. And so we've got 4 different protocols that are supported by this system. There's, of course, 9P. There wouldn't be much point in talking about it here if it weren't supporting 9P. And of course, that's sort of what we think of as the native one. There's an integrated NFS version 3 server in there as well. Now, at the time, I kind of did a little bit of debating about whether to go version 3 or version 4. But so many of the applications and customers that we had were primarily in environments that only supported version 3 at that time. And there were some things about version 4 that I wasn't sure quite how easy they were going to be to fold into this, that it just seemed to make sense to implement version 3. Though I will point out there are a couple of things about version 4 that are actually a little nicer for us. Version 3 of NFS, of course, is based on the traditional Unix picture of user identification. Integer UID GID. Plan 9's structure is expecting a textual user identification. That means if we're going to do anything with NFS in a Plan 9 world, we've got to have something that maps. Turns out NFS version 4, if I remember correctly, does support textual user IDs. Now, the flip side of all this is NFS tends to expect some things we don't have in Plan 9, like links. Now, theoretically, if you look at the spec for NFS, The links are optional. You don't have to have either hard links or symbolic links. But if you run any kind of system that expects to speak to NFS and do something with that, it's going to expect there to be links. I learned that the hard way. I did not have links. I then mounted this onto a Linux system and started trying to do a big compile and discovered the compiler expects links. So I've got to figure out how am I going to manage links in Plan 9. Interesting question. So these are the two protocols that are being used to access the file level of granularity. Now for the block level of granularity, at Core 8, of course, we had the protocol AOE for ATA over Ethernet. And this gives you an Ethernet frame level description of requests for block access, both reading and writing. That left the question of the object storage protocol. Now, rather than attempting to re-implement SCSI OSD, I added an OSD extension to AOE as an experiment. So the amount of experimentation that has been done in testing with respect to the object aspect of this is very minimal. But it has been used, at least in some basic testing, both as an AOE target and as a file system target, sharing the same storage space. Now, another thing about this that ended up kind of falling out interestingly was I didn't really feel a need at this point to attach a root to the superblock. And part of this evolves out of the idea of I want to use the full path name as the identifier and hash it. As a result, I don't really have to have a starting point that I begin the search from. That means I don't really have to have a root in the traditional sense. This actually makes it easy to have multiple roots. And so you could have multiple file systems sharing the same data space. This is one of the things that ZFS claimed was such a big deal. It's like, yeah, that's easy, yawn. Give me something hard. Now, when you first ream the file system, it creates a unnamed root. So it's designated //. So what happens is, if you have any kind of a name between the slashes, that's the name of the root that you're accessing. And then there's always this one unnamed one there when you first create it. The way that's kept distinct from all of the block access is that each of the metadata entries identifies a type. Basically, I use a quid like in Plan 9, where I've got a path and a type. Block accesses are one type, file and object accesses are the other. Object accesses don't have the prefixing /, file accesses start with the /. So that's how all three hierarchies, or all three granularities, are sharing the same space. All right, so the overall structure, some of it's fairly conventional. There's a super block, nothing terribly surprising there. Because this is doing hashing of the path names, there's a hash table that hashes path names to quids. Now, one of the things that comes up when people talk about this stuff, especially when you get into this world of, oh, hey, let's use objects for everything. There was this debate over whether you should implement objects on an existing file system or whether you should implement a file system on an object store. The former would be fairly simple. You just basically create a directory and name the files by the names of the objects. The latter would be along the lines of, I'm going to create a mapping from file name to object number. Well, who picks the numbers varies according to which type of mechanism you're using. If I'm living in an object storage world and I'm exporting an object interface, the client gets to pick the numbers. In a file system, I expect the file system to pick the numbers. So for that reason, I have an independent intermediate set of numbers, and those are the quids. So a path gets hashed to a quid. That quid then, there's another hash table that points it to metadata. So the structure of the overall storage space is the superblock, then those two hash tables, then we've got a free bitmap, and then we've got a reserved area for the metadata, very much like the region for inodes in a classic Unix file system, and then we've got our data blocks. Let's see, let me go ahead and illustrate some of this while we're talking about it. So I'm going to, I've got a console device here in serve. Now, I will warn you, I have some regrets about the Greek letters here. And you're going to really love this reason. My file server at home, the console on it is an actual literal VT220 terminal. I don't have the UTF-8 shortcuts on the VT220. One of these days, I will decide how I want to resolve that. Okay, so the command super just prints out the contents of the super block. And it's got the sort of stuff that you expect. It's going to tell us where to find the free space list. It's going to tell us where to find the metadata, where the blocks are. It's got the next number to use for the quid assignments. This stat is going to tell us whether it's dirty or clean, all that kind of good stuff. So this is the sort of thing that you tend to expect for that super block. Now, if I want to look at a path and I want to know what quid corresponds to it, the command P to Q is going to give me the path to quid translations. It's going to do the lookup in that hash table. And I'm going to go ahead and use the file that's the slides I'm looking at here. So that would be in papers theta-pres.pdf. And so that tells us that we are looking at quid 2881, which makes sense, considering that the next one to generate is 2882, and I copied this from my other laptop about an hour ago. So I haven't created any new files recently in this file system. Now, if I want to look at the metadata, there's a Q to M that will say, okay, given a quid, tell me which metadata entry has the beginnings of this. And that's where things begin to get a little bit more interesting. Let's see. The metadata, as you can see from this, there's a next pointer in there. Metadata is structured as a linked list. It's not a fixed structure. This gives us the flexibility to add things like symbolic links, or to have some entities that have the AOE major and minor device number, but not have the, say, UID, GID. So the metadata is actually kind of inspired by the extensible metadata in the VMS file system. And so this number that I've shown here, mapping the quid to the metadata, is basically the index into the metadata structures of the starting point, the head of the list. And if I want to look at the entirety of that, this will actually traverse the list and print out all the different values. And so, as you can see here, we've got things like the name of the file, a pointer to a next in the list that has to do basically with siblings. Well, this is our previous sibling. This is our parent. There's our quid path, version, and type, the usual mode, times, size, and the UIDs. Now, this gets us to the data storage part of it. So somewhere in the metadata for this thing, so we've got our path name, papers, Theta pres.pdf. Okay, that goes through the path to quid hash table and comes out with a quid number of 2881. That goes into the quid to metadata table, and that points to a metadata list that has a bunch of items in it. And these items are basically tag value pairs. So this is going to feel a little inefficient that we're literally actually doing string comparisons where we would normally just look at a structure member. But again, remember, this is research. I don't claim it to be production. I don't intend it to be production. I use it myself, but that's another story. Now, one of these entries in here is going to tell me where the storage space for this file is. And there are several possible labels that there can be, and dblock is one of those. Now, what I have to do is remind myself now exactly what the different numbers are. So let's go in here. The worst part was I was looking at this last night thinking, okay, I need to remember this. Let's see. Oh no, it wasn't in there that I could find that. These were names, not numbers. So I've got to go into here, and I need to look for dblock. Now, let's see. What's the best way to illustrate this? Yeah, here's a good way to do it. All right. So essentially what happens is we know from typical Unix file systems that you have essentially typically several trees in parallel of different depths. Common way of doing it, you've got an array of direct blocks, then you've got a pointer to an indirect block that points to a bunch of blocks, then you've got another pointer to a double indirect block. Here, everything is always going to be of the same depth. What happens is we will promote it if we need to. So the D block simply indicates a single block that this has. Now, in this particular case, we can get away with that just barely because our block size is 32K. And you notice the size of this file is 32,763, which is, we're 5 bytes away from having to promote this to a bigger representation. And what happens is this. So let's say I've got a D block here. This points to a data block. Now I make the file bigger. I've written 6 more bytes. So what it's going to do is simply allocate another block to become the new root of the tree, make the first entry of the root point to the data, make the metadata item point to the new root, and change the tag to say instead of it being a D block, it's a index. And now we've bumped to the next size of tree. And if we write off the end of that, then we'll do the same thing. We'll just allocate a new block to be the root, change this label down, now indicate we're a tree of depth 2. So that's the way the data blocks are structured in this case. So there's always only one entry in the metadata that points to where to find the data blocks. And the label on it tells you whether this is a data block itself or a tree of what depth. And with 32K blocks, and you can have a depth of 3, as you can imagine, you can get pretty big. That was part of the point of this, was what's the best way to deal with a world in which we're going to expect to be seeing large numbers of terabytes? How do we want to deal with something where we want a single file system to cover petabytes? That was part of the question that we were asking. And so this large block size was actually, it came out of that. The block size, by the way, in some of the earlier experiments was actually 64K. I had forgotten actually at some point that I had dropped it down to 32. I don't even remember exactly why. Now, of course, if you've got a whole bunch of these name value pairs in this metadata, there's likely to be some you don't care about. But that's fine, you just ignore it. So let's say that I'm doing a stat in 9P. Well, I'm just going to look for the metadata items that are going to correspond to what I need to return in the stat message. And I'll just ignore anything else. So if I've got a symbolic link, for example, and we've got a piece of metadata that says this is what this symbolic link maps to, then as far as the 9P view of that file is concerned, it's just an empty file. And that, in fact, is exactly the way symbolic links got implemented. There's a metadata entry called symlink, and its data amount contains the actual path. So let me kind of show you what these metadata items look like. So as I kind of showed here in the bit of code here for it, metadata item has a next, a type, a name, and then this union here. Now, the next obviously is just going to point to the next metadata item for that particular quid. So there's going to be our pointer to the next one. We've got a type here. That, just an enum that defines what the types are. And we've got a name here. So this is the thing like the D block or index or name or whatever. Those are the ones that we see over here in this printout. These labels over here are those textual names that are in the metadata. Now, if the metadata is a string and it's short enough, then we just put the characters of the string right here. If, on the other hand, it's a longer string, then what we do is we put a pointer in here to a place where the string gets stored. And because what we're doing is using an 8-byte value for that, well, if it's a string of length 8 or less, well, actually, because we need to make it null terminated, if it's 7 or less, then we'll just store it in place. Otherwise, we'll allocate it out in some other part of the metadata area and then just plant a pointer to it. For the most general type of metadata, we have a type we call a blob that essentially just says, point out to some bytes. How many of the bytes are there? Here they are. So it can be as general as you want. Now, part of the reason for this generality goes back to the objects again. In the object storage protocols, the protocol defines a set of messages whereby the client can set and request arbitrary metadata values. And so we can't really support objects in that way without having something somewhat, at least a flexible, if not an extensible, metadata representation. So that's where a lot of this comes from. All right, let's see. Now I zipped through a bunch of stuff. I want to see if I missed anything I wanted to say. By the way, I will mention one thing. I almost hate to mention it because I really don't want to highlight the similarity. The VMS file system, like everything else in VMS, was basically the inspiration for Windows NT. So NTFS has a very similar kind of metadata structure. That's the dirty little secret. I refuse to admit to it, however. Yes, that's true. I did make the mistake of saying it in a recording. Okay. We all know that what's on the internet lasts forever. Except when you want it to last forever, in which case you can never find it again. Okay, I've already kind of talked about this. This is the mechanism for handling the block mapping. So, kind of a quick summary of the experience with this. Okay, so first off, yes, it did work. I do use it. I have operated it with the same snapshot device that I talked about last year pretty solidly for about 10 years. There was, I will have to tell the story about a little period of time where something went wrong and something wasn't working correctly. I wasn't sure what it was. And I took a first glance thinking, oh, maybe I've run out of space doing the way the snapshots work. And my first glance told me that, no, I hadn't run out of space, there was another problem. And it took me forever to finally get back to coming back and say, okay, let me see if I can figure out what the actual problem is. Turned out the actual problem was I ran out of space. So I bought a bigger SSD, put it in there, added an option to the dev snap driver to basically resize, and much like the way Venti works, I just copied the first so many blocks and then the rest of it was where it went. So there is a window in my history that is not recorded because I thought something was wrong that wasn't wrong. Now, was this idea of hashing the paths a good idea? And you notice here I said probably no. I say probably because I want to hedge it. I still think there's a potential that there could be a win in terms of bypassing the walk process. However, 9P doesn't make that easy, and neither does NFS. When you do a walk in 9P, you need to build a list of all the quids that you visited. Well, if you're just hashing going straight to the endpoint, you don't have that. Now, you could, in theory, have metadata that points backwards up the tree, or you could store some other kind of thing. And I've thought about looking at doing that, but I've got to first do some performance measurements to find out whether or not that would be a win. But that's been kind of an annoyance. There's another problem in that I have so far punted on. As you walk, you really should check the permissions of each step along the way. Currently, I don't. Since it's only being used by me on my system, I don't really worry that much about permissions. But that's another factor that does need to be brought into play. The other part of the question, though, becomes, is there really anything that depends on that? Any 9P clients that really care about the intermediate quids when they do a walk? And it's not clear that anybody really cares, except for, okay, I can't walk any farther because this name doesn't exist. They frequently want to know where you left off in that process.
How about mounted table?
I'm pretty sure the mount driver takes care of that. I think that happens before we see it, but I won't swear to that. But that could be a place where it becomes important. Yeah. So that becomes, this was intended to be a next step of the investigation, was really to begin to look into this question of, can we get rid of this tracking of the walk process and just jump straight to the end? Or are the assumptions too deeply embedded? And then the question becomes, is it worth doing that change because of performance? Or is it just really not that bad? Does it really not hurt us that much? So that's one where, in retrospect, I'm not sure we got anywhere. I think there's still potentially something that could be there, but I'm not convinced anymore. I think the structure does work well for providing a unified storage. Providing a storage array that will support both block and file, and for that matter, object level access. I think that does work. I'm not happy with all of the integration of it. Having this one monolithic thing that has all of the protocol code in it and all of the storage code in it. Part of the reason for that originally was that because that file system component, depending on whether you're talking 9P or NFS, has different metadata it needs to talk about. I didn't really see a clean way of pulling those out and having a different file system interface here that would allow the file systems to see the devices both in terms of blocks and in terms of metadata. I'm not happy with that part of it. I feel like I should at some point go back and find a good way of doing that so that I can have AOE and the object and NFS as separate drivers or processes even, and then have all of the storage management separate, rather than having one big integrated ball of code. So I'm not real happy with that part of it. But it does work. I have used it for quite some time, not as heavily as I always intend to. It's one of those cases if I get home and go, okay, I need to remember to copy these things over to my file server, and then I don't get around to doing enough of that. But I was using it enough to eventually run out of space on a 64 gig SSD, by which point the cheap ones that were floating around out there were 480 gig. Which gets us back to the classic observation in the early Plan 9 paper. Manufacturers are creating storage faster than we can use it. I resisted believing that for a very, very long time. The more the time has gone by, the more convinced of the wisdom of that observation I am. If you look at most of the space that people use on their system, very little of it is any information they've generated themselves. It's almost always a copy of something else out there on the network. The vast majority of space that you're using is most likely copied from the network. You're just not using up the space for real that fast. And yeah, I ran out of space on a 64 gig device. At that point, you could almost not get 64 gig devices anymore. And the natural thing to buy was, well, almost 8 times as big. When I run out of space in it, well, I may still be around. We'll see. I mean, at the rate I used up the 64, it could be a while. So anyway, as I said, this was really just intended to be a platform for researching these kinds of questions. Not necessarily something useful, but I did feel like it was important to, as the saying goes, eat my own dog food by using the thing that I was working on and to see how useful and feasible it was. And remember, we're still on theta, and I want to get to omega. So there's still several directions I want to go. One of them, of course, is it does make a lot of sense to go to a log structure kind of design. The robustness that you get is really kind of hard to beat in other ways. And I think it makes a lot of sense to do that. As I've kind of already alluded to, this issue of path hashing, I really want to review that. And I've got questions in my mind about it. There are a number of elements that I'm going to kind of lump into the hardening, but I'm going to include things like those permissions checking that happens. That kind of stuff needs to be worked out to make this an actual useful real system. Performance, I have done very little, but a little bit of performance characterization on it. And the most expensive operation is removing things, which again goes back to they're creating storage faster than we're reusing it. So why are we ever removing anything? Okay? I don't care what the business school says. I don't care what the law school says. We shouldn't be removing anything. Just ask the guy who created the FPGA implementation of the Cray 1. He says, well, I've implemented this thing. Now I need some software to run it. Who's got some Cray 1 software? Crickets. They did finally find a pack. Nobody could talk to the drive. There was somebody who figured out some really clever, basically they built their own infrastructure. They had heads that they just recorded the analog signal off the heads and then decoded all that. That seems to be about the only Cray 1 software anybody can find. That's a scary thought. And then, as I said before, I want to split out the networking. I don't really like how it's all lumped together into one big thing. Now, as I've kind of already given away, the slide deck that I'm showing is stored on this file system. I also use this file system to capture some images of the eclipse on Monday. Let's see, I think there were about 800 and some odd images here. I'm not going to show you all of them. I mean, I do theoretically have 15 minutes, but no, actually I don't have that long. I have 7 minutes. I go through the whole eclipse in 7 minutes. No, I will show you a little bit of something, and let me see if I can remember which. Yeah, okay. Whoops. Does help if I'm actually on my prompt when I start typing. Let's see. That's the problem with having the delete key too close to the backspace. These are a few of the images of the limb of the sun as we're approaching totality. Now, this was all just goofing around. Okay, none of this was serious. I don't have really good equipment. Those images were actually a security camera that spoke over Ethernet, pointed at the screen that I was using for eyepiece projection. Okay? No real quality, nothing really all that good there. But I trusted this file system enough to put my Eclipse images on it to record them on there as it was going, given that this is probably the last eclipse I'll see. The next full eclipse, next total in the continental US is not for another 21 years. I don't really expect to be road tripping in my 80s. I'm not promising I won't, but I'm not expecting to. So I have a suspicion this might have been the last total eclipse I'll see. Unless I decide to travel someplace like Australia for one. Those are coming up relatively soon. There will be one in the northern part of Alaska. I think that one's in about 7 years. Yeah. Well, that's true. I'll now be up to Omega. All right, so any questions? Yes?
With path hashing, you use the duplication.
The deduplication? Yeah, I'm not attempting to do that. My thought is that, like the snapshotting, what I'd really want to do is make that another layer that this could sit on top of. So that if I want to get deduplication, I can do it that way. Yeah.
Yeah, so I noticed one thing that I thought a lot about when I was putting together GEFS, which I didn't hear anything about in this talk. Do you make an attempt at being crash?
No.
Okay.
Now, what's interesting is that it has successfully survived a number of crashes. You know, it sits there running on my file server all the time, and if we have a power glitch or whatever, then it in fact has done that. But it's never under particularly heavy load when that happens.
And
so
it's running on your snapshot device. You can just roll back.
Exactly. If I had to, I could always go back a day. So I haven't really made any great efforts in that direction. A lot of that I felt is really where I would begin addressing that in the log structuring kind of design. I felt like that would be the place I wanted to really put the effort when it came to the robustness. Yes?
I noticed copyright notices on top of some of those files.
Oh, yes.
I was wondering if there's any plan on releasing this publicly at some point.
Well, these are the 3-clause BSD licenses. So the intent is that anybody can use it.
It's on sources, contrib.
Yeah, I do have it. Now, the version that's on contrib has a couple of things that may get in the way of you trying to actually use it. And I will see what I can do about figuring out. I'm not even sure how to attach to sources anymore.
I thought it was gone.
I mean, I know that the web interface to it on 9p.io is there, but I don't know if you can talk to it with 9p or not.
9p.io, at least on 9front, will connect to it.
That's good.
Yeah.
9p.io.
So
It's in our 9fs.
And now, of course, I have no earthly idea if any of the authentication stuff got ported along. Remember, back in the day, you would go and send a note to Jim or Jeff or somebody, and they would put you in the auth server so that you could get to contrib, and you could put stuff in. I have no earthly idea if that's still accessible in any way.
You need to talk to David the Columber.
Yeah. But I say that mostly to say that the copy that's on contrib is very close to what I'm running here, but not exactly the same. So if you are interested in trying to do something with it, let me know and I can send you more updated code. I would like this to be treated more as a prototype and as research. And if somebody wants to do something serious with it, take the concepts and the design and implement it from scratch, much like the talk we had earlier about Venti. I'm happy to be the one who does the prototype and leave it to someone else to do the production version.
That sounds reasonable, but are you really sure you want the successor to be implemented in Scratch?
I won't claim any connection to it.
So one other small question. How are you laying out the metadata and other small bits of hash table entries on disk?
So basically what happens is the region that is used for that, I still interact with it in terms of 32K blocks, but I allocate it in smaller units. So the metadata itself, the main metadata structure, as you notice, is a fixed size here. And yeah, it's what? Yeah, 32 bytes. And so for all of the items that this sort of works well for, integer values, short strings, and so on, then they're just allocated in 32-byte chunks. For larger chunks, then there's essentially what it boils down to is it sort of rounds up to a multiple of, and then just says, okay, let me grab one of those.
Got it.
So in effect, the free list / free bitmap is just finer grained in those than it is for the data blocks.
Got it. Makes sense.
Yeah.
Have you thought like how systems like Venti fits into this picture? Like
so
instead of hashing paths, you hash the data.
Yeah, I did not try to think about integrating it with Venti, partly because again I was sort of thinking in terms of the snapshotting type driver being the replacement for that. Now, I did take inspiration from Venti in the idea of, okay, we're just going to append constantly in the design of that snapshot driver. Could this run on top of Venti? Yes, it could. It wouldn't be too terribly hard. You would pretty much need to have another data structure somewhere that essentially says which blocks have been copied to the Venti and which haven't. And then once a block has been copied to the Venti, you can actually free that block on the local disk, and now you can do your fetches from the Venti. That's more or less what Factotum is doing. And so you could do the same sort of thing here. But I've not really thought about what implications that would have and whether or not it would work well. Yes?
You mentioned the performance, that there are likely performance issues around dealing with paths as strings. Is that something that modern processors with string operations would be useful, or is the context change too much for that to be useful?
I think certainly in terms of the string comparisons for the metadata saying, all right, is this the metadata item I'm looking for? The string comparison part of it, if the compiler is able to detect that and turn it into a single instruction, that's going to ameliorate a lot of that. The structure, however, is still such that you're having to do a linear search through the list. and a comparison on each item in the list. Whereas when we have a typical fixed structure like an inode, then you just calculate the offset. In fact, that's done at compile time. And you just add that number to a pointer and take the data. So there's definitely going to be some overhead. And now whether that overhead is noticeable or not, I don't know. That would require a more thorough performance measurements and analysis than I've done. I did have a student one time I tried to get to do some of that. And unfortunately, this was a case of a student doing a summer research project and preparing a poster at the end. I had not had a chance to completely review his poster. We get to the poster exhibition, and I start looking at it, and I look at the graphs he's got, and I go, wait a minute, something's not right there. That just doesn't make any sense. So basically, I don't have any results from that bit of work. But the little bit of stuff that I did myself, I did things like, all right, let me see what happens comparing, let me mount this using NFS on Linux and do a big compile, and then compare it to something else. That sort of testing was at least ballpark competitive. To be honest, it's been so long I can't remember any more level of detail than that. The only numerical thing I remember from that time frame in terms of performance, so you remember I talked about sort of revisiting the overall structure of the storage network. And I've talked already here about the fact that I'm not real happy about the network and storage being integrated. Well, in the product that we had at the time, there was a similar integration that existed. There was a driver in the kernel called dev.sr. It had the entirety of the AOE protocol implementation and the entirety of the RAID code, all in one driver. And I felt like, the time had come that it should be split apart. And so one of the projects that I did is kind of in this larger context was to do exactly that. Take it and split it into two pieces. The idea being that you could now have things that lived in between the two if necessary. But one of my concerns was, would doing so introduce performance issues? So once I had done that, I was able to, in doing so, I was able to allow for a little bit more general configuration. And so what I did was I configured the storage side to work with a null device. And so I was only testing the protocol part. And I was able to saturate two 10 gigabit links between a Linux host and that server. So I felt like at least that part of it, I was justified in saying, yes, you're not going to lose anything to break those apart, and you're going to gain some flexibility in doing so. Unfortunately, even at the time, I had my doubts about whether it would ever be picked up as part of the product line, and it merely remained part of research. Yes?
So I was running 9atom until like 3 years ago, and at one point Eric had put this in the tree.
Oh, okay, cool.
And he was very enthusiastic about it. And
He was in the office next to me when I was doing it.
He was encouraging me to try it, and I had a long history of stuff inventing that I didn't want to,
right.
deal with moving over. But my question at the time, which I guess is still relevant, is looking at it sort of the Venti protocol from the other end. If you already have this object store model for it, could you, essentially point fossil at put a Venti interface, server interface on this, using the same sort of object store underneath?
I think in principle, yes. I don't know of any particular reason why you couldn't. So if you sort of imagine the hashes as just strings that are names for objects.
Right.
And you use those outside of the root namespace, that is, without any leading slash, you treat it like the names of objects, and you just treat that string as a name, then in principle, yeah, you could basically make that the object. Now, another way you could do that might be to say, that's probably the best way to do it, because you want to be able to look it up by that name very quickly. And so you really want it to treat it like that's the object number. Now, I'm trying to remember. I'm pretty sure that at least the prototype that I had done for the AOE object protocol would not have supported a number that large. But that would be an easy thing to model. I mean, the experimental OSD layered on top of AOE was just, hey, let me just throw something together and see what works. There wouldn't be anything too terribly difficult about extending that to allow for an object number that could be the hash. And then, yeah, this could then become, that part of it could be the Venti, and then you could also have the file servers. All of it, yeah, again, could be in the same pool of storage. So yes, in principle, it could. It would take a little bit of changes, but it would be doable. Any other questions? All right then. Well, thank you, and we are ending at 3.
So yeah, we're not going to finish yet. We have another few small sessions. Can I have like a very quick white talk?
Yeah. Oh, absolutely. I'm going to, yeah.
All right, test. Okay.
I can tell you if it works when I have those headphones in.
All right. So I'm Yaroslav Kolomiyets. This is unscheduled talk. I was inspired by talking to some people yesterday to actually give it. So this is about presentations in Acme, right? So two slide scripts, and this is the first part, and the how to get the rich text would be a second part. So the slide scripts are actually inspired by Russ Cox's talk. Is actually very old concept, right? So his tour of Acme, he used this same set of scripts basically to give that talk. So this, I think, over a decade old now. So I'll talk about that really quick and focus more about mixing fonts in the same slide. So changing slides, the slide plus, slide minus. I walk really quick about through it. It's really, really simple Acme script, which reads the tag, sets the name. So it takes argument the slide name, expects that same directory to contain that file, load it, and make it displayed. So it works like if I say slide title, in the same directory I have a file name title, it will just replace this window with the contents of that slide. And the slide plus thingy, so let me just go back here. The slide plus would be a slightly different, hold on. Yep. It takes a look at current window, the title of it, tag of it, allocates the file index, which expected to have all the slides. No, not here. Here. All the slides listed one per line in that order, right? And look up the next slide and display it. Yes, call the slide script. And slide minus is the reverse of it. It does exactly the same, but displays a previous slide, right? So to have it working, I usually have the guide file next to those index files, which allow me to set up the proper font I intend to display those slides in, and then basically, or have an index somewhere, and then start presentation, and just go through the slides by middle clicking on this slide plus, slide minus. So we observed many folks yesterday use this kind of scripting, which nice to see. I also tend to use it myself a lot for internal presentations. So this particular presentation has nothing to do with the subject of the talk. It's just a display of how we use the scripts. So another part, second part of my quick talk is the getting the mixed font. So Russ Cox also inspired this for my slides, although the way he did differs slightly from how I did it. So how he did it, was to use the private range, Unicode private range, to map new fonts or say like related fonts into that range and replace the code points of his text to use those ranges instead. So the downside of that approach is that the text is not readable in anything else but Plan 9 systems, right? With using that particular font with mapped ranges. So I did a little bit of digging. It turns out the Unicode itself has code points for different symbol variants, like displaying shape of A in italics or in bold, or the intention of that, as Unicode folks put it in the standard, is to have the typeset dependent semantics displayed properly, right? So whatever it is, whether it's like mathematical formulas or physical formulas where the bold and scripts like have semantical meaning, right? So where it cannot be changed when you change the font of the entire presentation, right? So this was the intention, but we can actually use this fact and create something like this, right? Within the same text, we can mix up different fonts without actually relying on rendering system to somehow change those fonts for us. We can just say that this text must be bold and there is no way around it. And the system, Unicode compatible system will just do it. And it's not dependent on like Plan 9 or Acme. I can just type it in terminal, Unicode aware terminal, in say the, it will be still readable text, and you can even, I don't know, can you see it? There will be different fonts too there. So this is my approach to multiply formatted text. So how I did it, yes. So I went through all the standards, Unicode standard, found the code points. They are not always the contiguous ranges. So basically I need to map from what I found to what I want to be. For example, for bold, this is pretty straightforward range, yes. Almost continuous. So these letters are not outside of some range, so we need to translate those differently. So on the left, we see the regular font. On the right, we see the corresponding mapping in bold range. And same for italic, and same for bold italic, and Helvetica variants, serif variants, and monotype, and segmented display if you're into that kind of things. So this is basically a bunch of TR scripts, but the way you use it is you select a phrase if you want. You call that script T font, say Helvetica italic, and you filter and you get your font. If you want to change it back or change to another font, you first reset the formatting. So there is another one which is translates it back to regular, and you can experiment with the looks. Yes, so you can do bold, for example. Or this was a, let's do HB. This would be nicer looking thing. Right? The other part is, okay, I almost sure that none of the standard Plan 9 fonts will be displaying those ranges correctly. Yes, so there might be some fiddling done. So best font, I think, available with best Unicode coverage is Symbola, right? But this is not a problem, as I have a solution for that as well. So I was looking into what I'm relying here mostly is the fallback logic of the macOS itself. So this font SRV on Plan 9 port, it uses the macOS font logic, yes, and rendering of the fonts. And but this is still not ideal. If you look here, this can be like looking really weird. What if you want to control that? Like I don't want to solve that for macOS, but for Acme or Plan 9, this is actually very easy, since fonts in Plan 9 are text, right? So this is the description of font format, which basically tells which ranges can be displayed by which bitmaps, yes? So even for some and some you can combine the phones within the can combine subphones in single bigger font. Yes, even within the Plane 9 distribution, it can be like Latin variant of a font and Unicode variant of a font, which includes more ranges but more like memory hungry. Yes, for those times when that still mattered. Today is not a problem anymore, right? We can include the whole Unicode range in one font and don't bother thinking about memory. So that brings us to the third topic, how to make those fonts. So I'll show you an example of a mixed fonts I came up with. So this is a Go font, Go regular, used as a base, but certain ranges related to those which you saw in the TR scripts, which are represented by another font, like Go Mono, for example. Mapped few ranges from Go Mono, few ranges from Go Bold, few ranges for Go Italic, and Bold Italic. So basically knowing these numbers, and they are never changed, they are in the standard, you can come up with all kind of font mixes. So I have this font mix awk script, which takes a base font and whatever you want for monotype, whatever you want for Bold Italic and Go Italic and Italic and Bold Italic, and basically filters, creates this mix. It just, whatever variables you have there, it just sticks them in and produces the output. And I'm using, instead of using the font created by Font SRV directly, I'm using these mixes instead. For everything, I'm just using Acme with those mixes. So I just solved this problem one time, and I never need to think about that again. So yeah, I think you can. Yes, both font mix and the TR script, you can find it in my contrib directory. It's YK character, I think. Yeah, I forgot to type it in here. So, and sources, contrib, YK, lab, font mix. That's the path where you can find this if you find it useful. And that concludes my lightning talk. Right, do you have any questions? Okay, no questions. Cool.